Welcome everyone to today's webinar, LED Lighting for Fluorescence Microscopy, a Sustainable Illumination Option, presented by Excitation Technology Corporation and hosted by Photonics Media. My name is Sarah Weiler, and I'm the Photonics Media Webinar Coordinator. I would like to introduce today's presenter, Dr. Kavita Aswani, Senior Biomedical Application Scientist at Excitation. Aswani will be speaking today on advancements in LEDs for fluorescence microscopy. If you have any technical issues during the webinar, please log out and log back in to rejoin. A recording will be available on the Photonics Media website shortly after the presentation. You will all receive a link to that. So if you have a colleague who is unable to join us today, please let them know that the recording will be available. We encourage you to ask questions throughout the presentation. Just type your question into the questions box on the right side of your screen, and our presenter will respond to as many as possible at the close of the presentation. And with nothing further, I would like to introduce our speaker, Dr. Kavita Aswani. Welcome, Kavita.
Thank you, Sarah. Okay, I'm ready to start. So good morning, or good afternoon, or good evening, depending on which time zone you're in. I am Kavita Aswani. As Sarah mentioned, I'm the Senior Biomedical Application Scientist for Excitation Technologies, and I have been in this position for over 10 years now, which kind of gives away my age, but hopefully that's not too bad. So the question here that I wanted to talk about is why use LEDs? Now, over the last few decades, our light bulbs, our TVs, our gadgets at home have all moved from lamps to LEDs. And as far as the microscopy world and imaging world, that has also been in the last decade or so that you started using more LEDs than lamps. But when they were initially launched, it was not perfect and it had a lot of issues, and I will discuss those and also how we have come about with a solution to address those issues. So why would one use LEDs versus lamps? And the lamp could be a xenon lamp or it could be a mercury lamp. So lamps have flicker just because of the inherent properties of the way it produces its light. LEDs don't have flicker because it's a uniform voltage that allows the light to be emanated. LEDs have instant on and off. Lamps require warm up and cool down time. I remember using a HBO lamp at my advisor's office, and she said, make sure you turn it on, wait for about half an hour, and then do not turn it off or the thing will blow up. And she basically scared the life out of me. So I was scared of that lamp. LEDs are simple on and off. Push a button, electricity flows through, light comes out. Push a button, it stops, and light stops coming out. With LEDs, you have a slower intensity loss over time, whereas with lamp, just because of their inherent properties, you end up losing about 30% of the initial intensity within the first 400 hours. And most of the lamps need to be replaced between 100 and 2,000 hours. So you have to have a stock of lamps, and depending on the equipment you have, you may have to have a professional to actually change it, change the lamp. LEDs are inherently more stable. LEDs also have repeatable output power because of the stability. Every time you turn it on, you know you're going to get the same power as before. With a lamp, because you don't know when the intensity is degrading, you have to be aware of what power is that's actually coming out of the lamp over time. Long lifetime, between 10,000 and 25,000 hours. A lamp, like I said, is between 100 and 2,000. LEDs, from a study that I did a few years ago, seem to be less phototoxic to cells than lamps. And I can send you the link to that paper if you're interested in more details. But it was very preliminary results that showed that cells are happier when being imaged by LEDs versus lamps. And there's one where a worm actually stops moving when imaged with a lamp, but he continues to wiggle when imaged with LEDs. LEDs use less power. They use less electricity versus lamps. There's zero mercury because it's not a bulb. There's no mercury or anything to be handled as far as waste and as far as getting rid of it, which actually costs money in most labs. And because there's no mercury, there's a lower green footprint, whereas lamps have a larger green footprint as far as being environmentally sustainable. With an LED unit, there's no consumables. With the lamp unit, you definitely have to have bulbs to replace when the lamp intensity degrades over time. And LEDs also have an option to select different wavelengths. There are broadband LED options, but there are also selectable LED options. Whereas in a lamp, you get the entire spectrum and you have to use a filter wheel in order to filter out the light to excite the fluorophores of interest. So just to give you an example here of how the lamps degrade over time. So lamp, you take out a new lamp, it's degrading within about 10 months. You got to buy a new one, it degrades. Put in a new one, degrades. Put in a new one, degrades. So this is just showing you the difference between the lifetime of an LED, which goes on and on and on for years, versus a lamp when you have to actually replace it at some point because the intensity goes below what's acceptable for your experiments. So cost of ownership. If you look at an HBO, which is your typical old-fashioned black box that has that has the filament bulbs. If you look at an Excite 120Q, which is also a lamp-based system, and you look at a LED system, this is one of our older LED systems, broadband, and then this is one of our newer LED systems that has a lot more power, which I will talk about in a little bit. So with some of these systems, you have replacement lamps, you have mercury content, you have to buy the lamps, you have to replace the light guides because you're getting the entire spectrum going into the light guide from the bulb, the UV and the IR wavelengths will end up degrading your light guide over time. And there's the cost of the light guide. Bulb disposal, most places will charge you for getting rid of your bulb. And then there's maintenance costs as far as being able to replace the bulb and the time it takes to replace the bulb. For HBO, you need somebody who's technically apt to change it, whereas for one of our lamp systems, it's just a put it in like your light bulb at home and shut the door. It's pretty easy. So if you look at the total cost over, let's say, 20,000 hours of being on, here are your actual costs of using an old-fashioned HBO, a lamp system that we also provide, an LED system, and an LED system with a light guide. So what's the issue? Why haven't we, look at this slide here. It's a no-brainer. Why hasn't everybody moved over to LEDs? Well, we did try early in the, like 2010 is when I first launched an LED product from Excite. And, it has its challenges, but the major challenge was that this is a spectrum of a mercury lamp, and these have been used for decades and decades. And a lot of the fluorophores that are used in the labs were developed around the peaks here that the mercury lamp has. Problem with LEDs initially, between the 500 and 600 was a green gap. And the green gap meant that you could not use LEDs within this green region in order to excite your fluorophores, which emit in the red region. So this was a challenge initially. And also LEDs weren't bright enough for low light level applications, such as fluorescent in situ hybridization. So what is the green gap? It's basically lack of semiconductor material that emits light between the 500 and 600, thereby allowing you to use green light to excite your fluorophores that will emit in the red region. So there is just no semiconductor material in that region, and this is an issue for the fluorophores that emit in the red and that are excited in the green yellow. And lamps and lasers were used traditionally for these wavelengths because that's what they were developed around. That's what the fluorophores were developed around. So poll question 1, please.
All right, so attendees, I'm now going to launch the first poll. The question is, have you switched from lamp to LED? The possible answers are yes, no, or I want to. I'll give you a couple seconds to respond. All right, I'm now going to close the poll and share the results. So 58% said yes, 22% of you said no, and 19% of you said I want to. Thank you very much. I'm going to close the poll.
Excellent. That's good to hear. So, excuse me, going back to a mercury lamp, and this I have zoomed in to be between the 500 and 600 region, you can see these nice two peaks, right? So lamps have the nice two peaks around which the fluorophores were developed. Our first LED product, which was launched, this was the power of the LED in the green gap between the 500 and 600. So as you can imagine, it didn't take off very well. And over the years, and actually now it's pretty much monthly, that LEDs are advancing so rapidly that things basically change all the time. And especially with Excelitas on our R&D team, we're making progress like pretty much every month to increase powers of LEDs. So our next generation, again, a little more power in the blue graph here, but nowhere as close to the lovely peaks that Mercury had. So we did suffer with, and not only us, even other manufacturers suffered with this particular region. We fast forward a few more years, and yeah, we're getting bigger, better. And so what we then decided to do is we had to get a bit more creative to get the peaks that are required, the peaks or the power that's required in order to fill up the green gap. So phosphor conversion has been used for decades, and what that encompasses is using a blue LED, which is right here. And what that does is it excites a phosphor, and the phosphorescence or the emitted light from the blue excitation gives you a nice curve between the 500 and 600. So what we did is we actually used this technology, and instead of using a blue LED to excite the phosphor, we used a blue laser to excite the phosphor. And this was the result. You can see now that we're getting a lot closer to the mercury peaks than we were, of course, in the beginning, which was the green graph. So we're getting there, and we're getting stronger every time. So here now, if you look at the spectrum of a lamp in the purple, and you look at the spectrum of one of our newest products, which is in the dark blue or black, you can see now that we're pretty close to where we should be as far as the mercury peaks. And yes, you still have the mercury peaks that are very peaky, for lack of a different word. But if you look at the area under the curve of our 500 to 600, that is more than sufficient for exciting a lot of the fluorophores in this region. So this is great. You know, this is the actual power that that comes out of the light guide. But what's happening at the actual sample plane? So for that, we went to a Olympus microscope, and we just focused on the green gap excitations, which would emit in the red, Texas red, Psi5, and Psi7. In the black, you see one of our new broadband LED products. In the blue, you can see one of our own bulb products, and that was our benchmark, is we wanted to be as good or better than our own bulbs. And then in the gray, you have a competitor. So you can see in Texas red, our LED system with LED laser hybrid drive is doing great. At Psi5 as well, this is our laser LED hybrid drive. This is our own bulb system. And again in Psi7, LED laser hybrid drive and our own bulb system. So just to confirm things, we moved to a different scope because all the microscopes have different light trains and work differently as far as what actually gets to your sample plane. So we tried another one, and we covered all the way from DAPI to Psi7. Again, in the black is our laser LED hybrid drive. In the blue is our own bulb system, and in gray is the competitor. And as you can see in the size 7, which is all the way in the 700-ish excitation region, our competition doesn't have many solutions available. So as far as having a system that can have the green gap filled with the laser LED hybrid drive, you can either have a broadband system, which is the gray graph over here. And what that is it releases all the colors, and you have to rely on a filter wheel in order to narrow them down to your fluorophore of choice. That's good. That's just like a bulb would be, but we have the power now. The other option is to have a switchable wavelength system, which you can see over here, that can go all the way up to the 700 and sometimes even beyond. So if you want higher, faster throughput, so you want to turn on your violet and image in blue, turn it off, turn on blue, image in green, turn it off, turn on green, turn it off, turn on red, turn it off, and then switch to another cell or another well in your well plate or a different slide, you can get through all those colors going on and off very quickly, because it's not relying on a filter wheel, and it's not relying on lamps being turned on and off. So you would use a selectable wavelength system with separate LEDs if you wanted higher throughput. I think this is the next poll now.
All right, attendees, I'm going to launch the second poll. And the question is, would you rather use a broadband light source or a switchable wavelength light source? The possible answers are broadband or switchable. All right, I'm going to close and share the results. 29% of you said broadband, 71% said switchable. Thank you, I'm going to close it.
That's great, thank you. So just to summarize as far as the applications are concerned, what are the benefits of LED? You have less downtime. You don't have to go get a technician to replace your old-fashioned bulb, or you don't have to go to the closet and get one of the excite bulbs to replace, and you don't have to stock up on them either. You have more uniform and stable illumination, but more importantly, you have repeatable exposure. So you know that every time you turn on that LED, the sample at your sample plane is getting the same amount of power. And that's more important than, than basic stability. It's more about the repeatability, so you know what your sample is being excited with every single time. I mentioned that if you have a switchable LED system, you would have faster throughput. I mean, everybody wants that, but obviously with a switchable LED, there's different electronics, so it would cost a slight bit more. And LEDs have advanced to the point now where you do have enough power for FISH, which is fluorescence in situ hybridization, where you're labeling parts of DNA with a fluorophore and the signal is very low. So you need a very bright light source in order to excite these fluorophores and get a meaningful result. Fura 2 is a calcium application. And with Fura, you're using 340 nanometers and 380 nanometers, which traditionally only xenon has been able to do. But now there are LEDs that are able to excite in the Fura region. Size 7 and beyond is between the 750 and the 800. A lot of people are moving to a lot of the infrared dyes, such as IR 800, and there are LEDs available in those regions. And then stereo microscopy. And in stereo microscopy, you basically have a microscope with a massive viewing area. So you can have worms or Drosophila or whatever in a big area at the bottom of a massive lens. And in order to illuminate a big area, again, you need a very strong light source. So LEDs are now at the point where all this is possible. It wasn't in the past, but now it is. So other than that, we can also use, there's also growing demand in analytical instrumentation, so such as fluorescence microscopy or microfluidics, where you have fluid full of cells or molecules that is going through some sort of liquid network. Your fluorescent slide scanners, your plate scanners, and especially with all the pathology going on recently, there is a lot more demand in being able to move things quickly as far as testing. And of course, there's microscopy that I talked about, as well as DMD, which is a digital mirror device that excites, that allows you to point the light to very specific portions of your cell or your slide. It's not only limited to analytical and microscopy applications, it also extends over to endoscopy, surgical visualization, and surgical microscopy. And along with your white light that a surgeon uses in this device over here that he's holding, along with white light to go into a body cavity, um, they also want to excite fluorescence now. So that's either UV or it's infrared, but there's also a fluorescence angle to endoscopy. And just to show you an example here, typically in endoscopy and fluorescence visualization, what you would use is this blue curve, which is a xenon lamp. That is traditional, it's the gold standard. So this blue curve has a nice flat curve between the 300s and the 750s. Again, this is a lamp. So if you did want to extend it all the way out beyond 750, chances are you'll be burning your liquid light guide. And similarly for moving more into the UV. In the purple here is a white LED source that is used in some applications. But what I wanted to focus on is this red graph over here. And what we've done is instead of RGB, red, green, and blue, all in one, like the xenon, we have separated it out into blue, into green, and into red. And what that helps you do is it enables you to match the power of xenon, but it also enables you to alter the RGB according to the color temperature that you want. So I'm looking at the white on my screen here, and that's a completely different view for me than it would be for Sarah or for anybody else sitting in the audience. Your white and my white depends on our eyes. It depends on the camera that you're using in order to get your endoscopy images. And with a unit that has RGB that's separate, you can actually balance the R, the G, and the B to make the white that you would like, because white obviously is made of a lot of colors, including red, green, and blue. So just to summarize, where is it? Yeah. LEDs no longer basically have to suffer from the gap. The green gap did exist between 500 and 600 nanometers, and it was a massive challenge for a lot of companies and a lot of industries. But in our case, with the laser LED hybrid drive, you can get the closest spectrum to lamp output, so you can excite the fluorophores that you want. You can also have a bright green in order to create an RGB system with the color temperature that you want. There is no lamp replacements, therefore no mercury bulb disposal costs and no stocking up, especially with the old-fashioned ones. Those ones die within 200 hours, and you need somebody specialized in order to change them. And with LEDs, you can keep your fluorophores and cells happy and lasting longer for your imaging experiments. So I think that's the end for me. And as usual, I talked very fast. But if you have any questions.
That was great. Thank you, Kavita. So attendees, now's the time to enter your questions into the questions box on the side of your screen if you haven't already. We already have some coming in. So I'm going to start with, what about shorter than 365 nanometers?
Sorry, what's the question?
What about shorter than 365 nanometers?
So we do have a 340 as sorry, there are 340s that are available out there. So the technology does exist. Was that
All right,
the question?
thank you. Mhm.
Okay.
Do you have any light sources that cover Fura in the 340/380 nanometer region?
There are light sources that cover that region. Do we specifically have? No, not as yet.
All right,
But
what light?
also I hear that people may be moving from Fura to other applications. So sorry, other fluorophores in the same application. So if you if you have a demand for any specific wavelength, please, let us know.
What light source can I use for about 800 nanometers?
So right now it's primarily lasers, but there are LEDs available. I don't think they're very widespread. But yeah, as of now, it's pretty much lasers that are being used. And you also have to remember that at that wavelength, if you're going with a lamp system like a xenon or any other lamp or laser, you're going to end up frying your light guide. So, you need to be careful about what kind of light guide you use for that application.
All right, thank you. Do you think in the near future the technology is going to go from LED to lasers to protect the energy losses?
Eh, Wishful thinking, I would hope so, but the laser costs are still pretty high. So, maybe in the next 20, 30 years that would happen. But as of now, the cost is a restriction and the electronics required to run a laser.
What is the role of IR doubling LEDs for green?
What is the role for IR
I,
doubling?
oh, sorry, hold on. I left out one word here. What is the role of IR doubling X tall LEDs for green?
So from what I understand, the IR doubling would be, using like a 900 nanometer to double the frequency to get half of that wavelength. So if you're using 1,000, for example, and you would do the IR doubling, you would get 500 nanometers as far as the emission. I'm not sure I understand the question.
All
So
right, well,
yeah, if you could email me with more details about that, I am happy to answer it.
yeah, all these questions are, Kavita's going to receive these. So if there's something that you want to make sure is answered, you can email the moderator, let me know. What is the typical coherence length of the LED?
Again, that one I will not be able to answer.
All right, what is the lifetime for LED light sources?
So the LEDs themselves, people say they can go between 50,000 and 60,000. But once you integrate them into a system such as ours, again, depending on the unit, it's between 15,000 and 25,000 hours, which is a lot. And
What are
and
the
and and that, sorry, that is on time, right? Because you're turning them on and off as much as you'd like. So it's not like a lamp when it's on all the time. Sorry.
No. What are the initial costs of a laser LED?
So again, it depends on the unit. So because we do all the we've our R&D team has created the architecture for one of these. Depending on the unit, it can go between 10 and 15,000. And again, it
All
depends on the accessories required and which wavelengths you need. But yeah, you can contact us for a quote and we're happy to help.
And if you're not sure how to do that, please contact the moderator as well. How do fish probes respond to LED fluorescence compared to mercury?
So similar now we're at a point where it is similar, but like yeah, in the past that was one of the issues. But now that we have the power, with our Xylus, for example, I have not heard of any issues from the field and from our testers.
All right, thank you. You're speaking to biological applications. What about imaging of fluorescent materials like quantum dots on film, for example? Do LEDs have enough power, especially in the UV or blue range, for quantum dot excitation?
So quantum dots takes me back like 15 years when they first came out, and I have not revisited it, except for in biological applications where lasers used to be used. I don't know the answer to that because I have not played with quantum dots in several years now. But from what I have seen over the years, I don't see an issue because if lamps and lasers were able to excite quantum dots, uh, I have I think our LEDs would be able to match them.
All right. Um, Last question. unless you can enter a couple more questions in here. We have time for them. But for now, can we use an LED light source of light sheet optics?
Sorry, can you repeat that?
Can we use an LED light source for light sheet optics?
Okay, that's a good one because I know that lamps are used for light sheet, but there's something about LEDs that has not allowed them to take off. And if you can send me an email with that one, I will get you more information from the light sheet experts.
Sure, and I'll make sure that gets to you.
Yeah,
All right.
I know it's being looked into, but I do not have a definitive answer about whether that was successful or not.
All right. Well, thank you very much, everybody, for your questions. Thank you, Kavita, for the presentation. I'm going to close the webinar now. Just a reminder that a recording will be available shortly. Everyone who registered will receive a link. So you will look out for an email from me. And again, these questions will go to Kavita. And I'd like to thank you all again for participating in the webinar. Thank you, Kavita, for the excellent presentation. And I look forward to you joining us again. Thank you,
Thank you.
everybody.
Bye.